Cool.
So welcome everyone to this presentation today. This presentation will be recorded and everyone participating in the recording will not be shown in the recording unless they ask a question at the end. So then I give the word to you, Diego.
Thank you very much, Shasti, for the introduction and presentation. So, my name is Diego Barbieri, and recently I just got a PhD at Norwegian University of Science and Technology. Today's presentation is going to deal with the research carried out at NTNU during these 3 years. The title of the PhD topic and project is Use of Local Materials for Road Construction, and study innovative stabilization techniques for crushed rocks. As a first image or input, I would like to portray this piece of advertisement that was posted by the Norwegian Public Roads Administration a few years ago. That is to say, trying to say, you need rocks because it seems like we are having a huge surplus of rocks. And of course, we would like to deal with these rocks in a proper way. And we'll see anyway during the presentation how it is possible to deal with this surplus of rocks. So first and foremost, let's have the overview about today's presentation. But by the way, we already had a presentation kind of one year and a half ago. So this presentation is going to partly cover those topics and of course the new topics that we have been dealing with during the other parts of the PhD. So first and foremost, I'm going to talk about again the motivation and the mission of the research. I'm going to talk about the unbound granular material, their properties, and the tests that we have carried out at different levels, that is to say in the laboratory, at the modeling level, and at the field test level. In the end, we can draw some conclusions and make some recommendations. So first and foremost, the project has been connected to the E39 coastal highway route, because this motorway route is incredibly important for Norway, from first and foremost from an economic point of view, because a lot of the goods and of course merchandise and products that are produced in Norway, they are usually freighted along this motorway. So today, if you want to travel from Trondheim to Kristiansand, it takes almost 20 hours. And of course, the goal promoted by the Norwegian Public Roads Administration is to diminish this travel time. Among the considered techniques, of course, one is to remove the ferry connections and replace them with fixed connections like bridges, and on the other end to to build an extended tunneling system. And actually, this research is strictly connected to the construction of these tunnels, because as a result of these tunneling operations, we are going to have a huge surplus of rocks. And of course, our goal from the sustainability point of view is to look for ways, methods that can enable the use of these rocks. So, of course, we have, of course, the rocks can be used in several ways, and we, as part of the, as we kind of in our department at NTNU, we have been focusing on how it is possible to reuse these rocks in the pavement construction, of course, at a local basis, so that the transport distance is anyway reduced. And in particular, we have been focusing on 2 layers of the motorway, of the road, that is to say the unbound layers, namely the base course and the sub-base course. When it comes to using these rocks in these two unbound layers, first and foremost, we need to check whether the properties of these rocks fulfill the requirements defined by the Norwegian code N200, that is to say the payment design code, and actually we do have two very important parameters, that is to say Los Angeles values and microdeval values, so that if our rocks are not able to meet these requirements, of course we cannot use the rocks as they are. But if they of course fulfill these requirements, then we are ready to use. We can of course freely use these rocks in the unbound layers. As a preliminary stage, as a preliminary activity to this research, of course, it was important to understand or actually have an idea about the geology and about which kind of rocks we can expect to find along the E39 Trace alignment. So we can see in this image that here in the kind of in the northern part of the motorway alignment, we have pink colors. That is to say granite granodiorite rocks, and actually they are and they are usually strong rocks. That is to say able to fulfill this requirements. But as we move here in the southern part of the alignment, of course we see that we also have other types of rocks. For example, sedimentary and metamorphic rocks, and actually the properties of this sedimentary and metamorphic rocks, they aren't good as the igneous rocks. So the basic question for our research has been how is it possible to use these weak rocks and of course use them with at a local basis. I mean, avoiding a transport distance, avoid any excessive excessive transport distance. So now I would like to highlight, or actually to remember that when we are dealing with rocks, or actually also called puck directly in Norwegian, we do need to remember, keep in mind that we have two mechanical properties. That is to say, the first one is the stiffness, or the resistance modulus, and the other one is the deformation. Both stiffness and the deformation, they are dependent on several parameters. The most important, for sure, being the stress level and the water content. And afterwards, the density, the grain size distribution curve, and the geology. So regarding our research, we actually have been considering this input. So for the stress level, we have followed the stress path suggested by the European norm. Regarding the water content, we have investigated two water content. The first one is 1%, and the other one has been 5%. That is the optimum moisture content. Density, we have been using a compacted samples, compacted for 30 seconds. The grain size is a distribution curve. Well, during the PhD, we have been studying a typical base layer, that is corresponding to this dashed line. And regarding the geology, we have collected 4 different types of rocks. Of course, that lie along the E39 alignment. So we have been doing several testings in the laboratory using the repeated Tri-axial load test apparatus. So the key point, kind of the key idea behind this apparatus is to provide our specimen with a stress level which is kind of similar to the stress level which is likely to be encountered in the real life during the real life of the road. So the specimen, of course, it is composed by our crash rocks. The specimens have been compacted. Then they are put inside the apparatus. Of course, there is a membrane that you can see here, and afterwards we fill this chamber with water. So that of course the water surrounds our specimen, and what's more, we can adjust the pressure of this water, so that we can actually adjust the tri-axial or surrounding pressure. In addition, here we have at the very base, we have an hydraulic jack, and actually this hydraulic jack can provide a deviatoric pulse, a deviatoric stress. So actually, by adjusting both the triaxial stress and the deviatoric stress, it is possible to understand properly the mechanical properties of our crash rocks. As mentioned before, we have been following the stress paths suggested by this European norm. So, according to this norm, according to this stress procedure called multi-stage low stress procedure, we have been considering first and foremost 5 sequences of stress. That is to say, of triaxial stress. That is to say, each sequence corresponds to an increasing value of triaxial stress. And actually, this is why you can see 5 different colors here in this curve. So that every curve corresponds to different triaxial stress. In addition, for each sequence, it has been possible to adjust the deviatoric stress provided by the hydraulic jack, so that each sequence in turn is composed by 6 steps. This representation is actually equivalent to the table described before. That is to say, they are the stress paths provided by this European norm. Of course, we get a lot of data, a lot of experimental data out of this experiment, and of course we need to be aware that there are some models we can actually use to interpret the data, and here we can actually portray some of the most famous or most important. The first one is the X and mono-speed model. We actually have a connection between the bulk stress and of course the resilient modulus. We also have other models like the Usen models and Usen and Witzig model. That is to say, other models anyway establishing a connection between the stress levels and the resilient modulus. Of course, these models are kind of they were found some years ago, but they are really reliable when it comes to describe the data, the experimental data, in a good way. The other important mechanical parameter I said before is of course the deformation, and experiment engineers, of course, our goal is to is to look for material that has the best deformation properties in the sense that the residual deformation, I mean the deformation that is of course responsible for rotting problems, is as little as possible. And actually it is possible to understand these properties very well with the Tri-axial test as well. And actually we have also some models that we can use to interpret the data. During our research, we have been considering the Coulomb model. Well, actually, the idea that is behind this model is actually simple. That is to say, if the permanent strain rate is low, is little enough, of course, we are in an area that can be considered elastic. If the permanent strain rate is actually too big, or actually exceeds a threshold that we have defined, then we can consider to actually be in the failure zone. Otherwise, we are in kind of middle zone, that is to say elastoplastic zone. Of course, again, as pavement engineers, our goal is to keep the performance of the road in the elastic zone as much as possible. Again, as well as for the center modulus, we also had some models regarding the permanent deformation. The first, the first two ones, that is to say the partial model and the Sweer model, they do establish a connection between the number of repetitions of the load provided by the vertical hydraulic jack, and of course the permanent deformation. While we also have other models like the height model and the Shenton model, which actually provide a connection between the stresses and the permanent deformation. Of course, I would like also to remember that more complex models combining the number of road cycles and the stresses are available as well. But we haven't considered this model because these ones kind of have been sufficient for us to investigate the cross shocks and what's more understand that the use of some additives that I'm going to talk about later has been effective. So now let's move on again and talk how we got and where we got the materials that we studied during our PhD. So we went to close to Bergen in the building site Statens, and actually while we were there, we collected three materials. Material M1 has math igneous origin, while material M2 and M3 they have metamorphic origin. Of course, the first thing that we made was to characterize them according to the standard tests. This is to say the Los Angeles test, and of course the micro-deval test. And as a result of this test, we could understand that material M1 was actually a good material, so that it's kind of a strong rock in the sense that it can be immediately used for pavement applications, while materials M2 and M3 they are not strong enough. So we need to find a way to improve the properties of material M2 and M3 in order, of course, to enable their use in the pavement construction. So our special stain, our question mark, is actually how is it possible to improve the properties of these M2, M3, or anyway of these weak rocks, of the rocks which are not able to fulfill the code requirements. So the first approach, of course, kind of simple from a kind of mind point of view, is of course to mix the strong and the weak rocks. It is to say mix N1 and N2, or mix N1 and N3, and then see which kind of relationship we get. Well, in this case, we got kind of a clear linear relationships when it comes to mixing the strong and the weak rocks, both of course regarding M1 and M2, and mixing M1 and M3. Of course, the other way could be to use additive. Well, today, when we talk about additives, we do have some technologies that are already available. For example, I would say bitumen stabilization, line stabilization, cement stabilization, just to mention the most kind of famous ones. Well, during our PhD, we have been investigating other resources, other additives that actually can be used, and these additives haven't been used that much for sure in Norway, and anyway on a world basis, and actually this is why it has been extremely interesting to investigate these additives. And actually, when it comes to these additives, the applications that the literature pinpoints is just referring to lime and silt. So actually applying this or actually studying the application of these additives to crush rocks is actually the novel content provided by the PhD research. So let's start and describe the first additive that we used regarding the crushed rocks. So the first one has been a polymer-based additive, and actually it is made of two components. The key idea, or actually the key properties of this polymer-based additive, is that there are polymeric chains that can actually merge with the silicates that are present on the surface of the rocks, and actually the more silicates we have on the surface of the rocks, the stronger connection we get between the additive and the rocks themselves, and actually furthermore, as another beneficial kind of property provided by this additive is actually that the rocks become the surface becomes impermeable, so that the water cannot penetrate into, for example, the base or sub-base layer. So the first results in the laboratory, well, they did confirm that the use of this polymer-based additive was actually effective, and we also investigated kind of the coating effect provided by the use of this additive. That is to say, we soaked the rocks with this additive. We wait some hours. I mean, we wait the necessary hours, the necessary time for the additive to properly bond on the surface, and then we made the standard test. That is to say, the Los Angeles test and the Micro-Deval test. And actually, as we can see from these pictures, of course, it seems that these additives, they do have a beneficial coating effect. The other additive that we have been studying during the PhD project is actually the lignin-based additive. The lignin-based additive is first and foremost a product that is renewable, and it comes from paper industry. It is non-toxic, non-corrosive polymer, and we need to remember that it is a water-soluble additive. Therefore, we need to pay attention when we are using such an additive. Anyway, again, first and foremost, we made some preliminary investigations in the laboratory, using, of course, the Tri-axial load test, and we could understand that actually the lignin-based additive had a beneficial effect. Since of course we can see that the reference modulus is higher here than the reference modulus attaining to the rocks which were not treated. Similarly to the previous case, to the other additive, of course, we also tested. We also made the standard test, that is to say the Los Angeles test and the microdeval test, after having soaked the rocks with the lignin-based additive. And again, the results are pretty much clear, I would say, since it really seems that we can really understand that both the Los Angeles values and the microdeval values increase, so that the additive does provide a beneficial coating effect. So, as a further part of our PhD research, of course, we wanted to make some modeling out of these experimental results. So first and foremost, we try to analyze, we try to interpret this experimental data according to the models that are available in literature. Let's say the models that I mentioned before. So in these following slides, we have two colors: that is to say the magenta color and the black color. The black color corresponds to the untreated material, while the magenta color corresponds to the treated material, whether with polymer-based or lignin-based additive. Again, in these slides we have two parts. One part just portrays the results with the lignin, and the other part of the slide just deals with the results connected to the use of the polymer-based additive. So here, for example, let's start with presenting the experimental data coming from, of course, the repeated Tri-axial test. So it's very clear that of course the experimental data connected to the magenta color, that you see connected to the stabilized rocks, to the treated rocks, are actually much higher than the recent models connected to the untreated rocks. And again, of course, we can also actually plot these results in a 3D plot. And again, the magenta colors, of course, are, I mean, the resilient modulus corresponded to the treated materials are actually higher than the resilient moduli connected to the untreated materials. So as mentioned before, first we followed the Higgs monism regression. Then we also modeled. Then we also displayed the results according to Usan model regression, and according to Usan model regression. Of course, whether you're talking about a surface like Usan model or Usan model, or you're talking about a line like in the Higgs monism model, of course it's always possible to see that the magenta color, that you say the treated material performs better than the untreated material. Here we have some parameters just connected to the regression analysis. The other key parameter, the other key mechanical properties, as mentioned, is actually the permanent deformation. Again, here first and foremost, we display the results coming from the experiments from the Tri-axial load test. And here we just portray the same results, but we have different values along the x-axis. For example, here we portray the ratio between the diatoric stress and the Tri-axial stress. And here, for example, we portray the ratio between the maximum diatoric stress and the Tri-axial stress. So the first model we used, we consider, of course, was the Barksdale model. So it's very clear that of course the accumulated vertical permanent strain here the magenta ones are actually much lower than the untreated materials. And very similar results we had if we considered the Fourier regression model. Again, if we consider a height regression model or Shenton model, of course the magenta data, that is to say the deformation, the permanent deformation connected to the treated materials was actually always much better than the permanent deformation properties connected to the untreated materials. Here we have some regression models. I mean the parameters, some parameters of these regression models. Of course, as a next step, we wanted to see how it was possible to model the repeated Tri-axial load test. So we built a finite element model, and actually, of course, the geometry is simple because the specimen is just a cylinder. So of course the most demanding task was to implement the right constitutive relationship coming from the experimental data. Of course, we considered the elastic part, and we also considered a plastic constitutive relationship, a plastic law, and actually considered two plastic laws. One is Tresca, the other one was von Mises. And actually, at the very end, we also considered a creep, kind of extra constitutive relationships. But we're going to talk about this anyway soon. So when we talk about plasticity or plastic laws, we need to define first and foremost the initial yield stress, that is to say equal to the deviatoric stress, because of course since the beginning of the use of the repeated Tri-axial load test, we always have both elastic and plastic deformation. And we also need to define the plastic tangent modulus that was defined by plotting the results of the repeated Tri-axial load test. Regarding the creep, of course, the unbound granular materials, they are not kind of viscous materials. But in this case, we figured out that if we implement such a creep relationship, it is possible to have a better description, a better match between the experimental results and the numerical results. So this slide actually portrays the results from the modeling and from the laboratory work. So here we have two rows. So the first row at the top, it displays the results connected to the use of the polymer-based additive, while the row at the bottom, it displays the results connected to the use of the lignin-based additive. The first column, it portrays the results connected to the use of the plasticity law according to Tri-axial law. The second column portrays the results connected to the use of plasticity, von Mises plasticity law, while the third and last column actually it displays the results connected to von Mises and Cree. So actually, let's focus, for example, here on this image. We can see that the distance between the three lines, that is to say the experimental data, and the numerical results is really close. So actually, it seems like if we use the von Mises plastic law and this kind of fictitious creep law, we have the best description of the experimental data according to a numerical model. As the last step of the PhD research, of course, we did want to investigate and assess the effectiveness of such additives in the field, because of course when we are making research, or actually when we are dealing with new technologies or new solutions, we always need to be reminded that modeling is one thing, laboratory is another thing, and of course the field, the real life is another thing. Of course, by matching all of these three kind of conditions, or actually how can you say, research field, or actually research contexts, we can actually understand the real use and the real value of what we are doing. So in this case, we carried out this test starting from May 2018, and we carried out this test in a quarry located close to Trondheim in Heimdal. And actually, the material which was available in this quarry is called, of course, for convenience sake in this research as material M4. That is to say metagabbro with greenstone. But anyway, what is important is that this material is actually a strong material. But of course, if we apply our additives, we can still see, we can still assess whether this material can get even better. So here we portray the images, the pictures that we took when preparing the test. So actually, the goal was to build three areas corresponding to typical base layers. Of course, one layer contains the lignin-based additive. The other one contains the polymer-based additive, and the third one contains just water. So here we have the other pictures, actually, which are able to let us understand better the main steps of the construction. So first we built our 15 centimeter layer. So of course we placed the material. Afterwards, we applied the water on all of these three areas. we applied the additive, the polymer-based additive on one area, and of course we applied the lignin-based additive on the third area. We mixed all this water, additive, and rocks together properly, thanks to the action of a proper mixing tractor, and afterwards, of course, we proceeded with the compaction. Then we placed another kind of layer. Of course, we repeated the operations so that the final thickness before the compacting action was actually equal to almost 30 centimeters. So at the end, or actually at the beginning of our field experience, this is how the areas look like. So here, of course, we have the section just containing water. Here we have the section containing water and polymer-based additive, and here we have the section containing water and the lignin-based additive. This is the aspect after 50 days. Of course, we can see that when it comes to the water, to the area, of course, the rocks are still kind of there, unbounded materials. But when it comes to the polymer-based additive and the lignin-based additive, of course, we can just from the eye, or actually sight point of view, we can see that there is a binding action. But actually, of course, we need to assess the results from a scientific point of view. From an objective point of view. So we carried out some daily measurements with a lightweight deflectometer. The idea behind the lightweight deflectometer is to assess the deflection which a plate undergoes when it is hit by a falling mass. Of course, this is a device that can be easily used just by a single person, and of course connected to the most traditional device, that is to say the falling weight deflectometer. This device is different, mainly in the sense that the investigated depth is of course lower, and of course because the impulse load force that is generated connected to the input load that is generated by the falling weight deflectometer is of course smaller. But still, when it comes to just understanding the properties of this 30 centimeter layer, this was a very good way to do that. So here we have the results regarding the stiffness evaluated by this lightweight deflectometer during the first 50 days. So in these slides we are portraying the untreated material in black color, the polymer material, the polymer-based additive in blue color, and the lignin-based additive in orange color. So first and foremost, is of course very clear that the use of the polymer-based additive is kind of a really effective additive. When it comes to the untreated material and the lignin-based material, well, it seems like they are kind of similar until actually we reach 30 or 35 days. So it seems like the lignin-based additive, of course, since it's also water sensible, it is water soluble. It is not kind of as its effectiveness is not as rapid as quick as the polymer-based additive. But anyway, we repeated these measurements after almost 4 months, that is to say in September. So after 110 days after the construction, and actually we saw that the stiffness regarding belonging both to the lignin-based additive and the polymer-based additive was pretty much similar, and of course much higher than the stiffness belonging to the untreated material. So it seems like the lignin-based additive, it needs some time to become effective, and of course we always need to bear in mind that we didn't have any bitumen layer on the top, so there was no kind of coating effect provided by the bitumen to the lignin, so that of course the lignin was exposed to rain, to natural rain, to rainfall. Similar results, of course, can be displayed, can be inferred as well regarding the settlement. So these are the settlements, again assessed by the lightweight deflectometer during the first 50 days. Again, the settlements connected to the use of the polymer-based layer of the polymer-based additive, they are the best ones, since we have the smallest permanent deformation values. And when it comes to the permanent deformation values after 4 months, again we have that both the lignin-based and polymer-based additive, they perform very well. I mean, similarly, first and foremost, anyway, much better than the untreated material. Of course, we also have kind of different or simpler methods to assess the validity, the effectiveness of such additives. The first one, for example, was to use the dynamic cone penetrometer, the DCP, and actually the way of using this technology, this device, is kind of simple. I mean, we just have a vertical rod. The conic end is placed on the top of our layer, and then there is a falling mass. Just falling down, and so hitting the cone, so that the conic end, the cone end can actually penetrate down in our base layer. So here we have a very interesting graph that portrays along the x-axis the number of blows, while it portrays along the y-axis the depth from the layer surface. So first and foremost, it's curious to see that when we come around kind of 12 blows, then we are able to reach the bottom of the layer, which was not treated, and of course we can continue hitting the cone and to get to the end of the treated layers. So of course this displays that this shows of course the penetration, the resistance provided to the penetration of this metal cone is of course much higher when it comes to the treated material than the untreated materials. And this similar graph actually portrays the number of blows which was necessary to reach the end of each one of the three areas. Of course, when it comes to the untreated area, almost 20 blows were sufficient, were okay. But then we needed almost 50 blows when it comes to the polymer-based layer to reach the bottom, and almost 46 when it comes to the lignin-based additive. Finally, we also decided to evaluate the rotting properties, evaluate, assess the rust, which it was possible to create by actually driving a 6-ton axle back and forth on each of these 3 areas. And actually, we drove this truck first and foremost 100 times, and here we have the results. And furthermore, we drove it back and forth again 200 times. So when it comes to the rotting, it is very clear that again the materials performs not really well. Of course, it's the worst one compared to the both lignin and polymer-based additive. So now we made some conclusions out of the PhD work. So to say, of course, that the isothermal alignment, it comprises a lot of geological conditions, a lot of rock types. So some kind of the strong ones, they fulfill the code requirements, while other ones do not do so. We have been investigating some additives and see whether it was possible to improve the properties of the crush rocks. And actually, we have been studying 2 additives. So this one was polymer-based additive. Another one was lignin-based additive. The first one, the polymer-based, of course, had a rapid effect. It even creates an impermeable layer. So it turned out to be effective. When it comes to the lignin-based additive, it turned out to be effective as well. But it needs time to become effective, and of course it is water soluble. So we need to take attention. So we need to pay attention and consider carefully the application of this additive. For example, we can first use this additive during a week when there is no rainfall, when there is no precipitation, and afterwards directly use kind of a bitumen layer to cover, of course, the base layer, so that the water cannot penetrate and actually worsen the performance of the layer where we are using the lignin-based additive. Of course, we can also consider some inputs for future research. So the first one is we have been considering four rock types during the PhD project. Of course, it can be possible to consider even more rock types to kind of to make more general to generalize the results that we got during this PhD kind of research or task. The other interesting point is actually to test the different additive mix percentages, because during the PhD research we have been investigating two mixing proportions, but of course when it comes to real life and use these additives in the most proper way, of course we strive to look for a percent for the optimum content of this additive. Another important aspect is, of course, to understand and describe the long-term behavior of the field test. And actually, we are going to replay the daily operation soon in May, so that actually we have the feedbacks from our field test after 1 year, and of course. We have decided how to use these weak rocks in the unbound layers, but it can be interesting, of course, as an input for the research, of course, to study also the use of these weak rocks in the road-bound layers as well. So thank you very much for your kind attention. It's been a pleasure, first and foremost, to take the PhD at the NU. Therefore, of course, sincerely thank professor, colleagues, Norwegian public administrations, and all the parties that have been involved in this huge process. It has been a really exciting task, and for the time being, I'm looking forward to continuing with this task and the research as postdoc researcher.
Thank you, Diego. And then it is open for questions. You can either ask questions orally or you can do it in writing.
Okay. Well, first, if there are any questions from the audience, of course, it will be a pleasure to discuss.
I cannot see that we have any written questions, but we have one from Andre Dawson. What is the cost effectiveness of your treatments?
Okay, yeah, so Andrew, thank you for the question. Of course, it is always something that we need to consider when it comes to real life. So let's say that when it comes to the lignin, we are almost around let's say $500 per ton, around, but of course it depends how much you are asking for, and this extra conditions, but of course it is just to have a general idea. When it comes to the polymer-based additive, well, the price per liter is actually around $20 US. And again, of course, the final price depends on how much quantity you're asking for, and of course similar matters. Of course, if we consider the price per liter, the polymer-based additive is of course much high. Is kind of much more expensive than the liter made of lignin. But when we are using polymer-based additive, we just actually need a little quantity compared to the quantity which is necessary when we consider the lignin-based additive. Or actually, just another interesting idea. In order to make our field test, the cost of the polymer based additives was actually double than the cost connected to the use of the lignin-based additive. But of course, as I mentioned before, as a further input to our research, we should actually try to play with these contents, and so look for the best content, of course, from time to time, from task to task and from construction site to construction site. I hope that these numbers have been useful to provide you all with a general idea regarding the price of these additive solutions.
this will definitely be interesting to follow up when we look at the whole of the E39 project. We have two more questions. Have there been evaluated other like PowerSem from the Netherlands?
So thank you for this question again. Well, actually, we did have some talks with these guys, and in the end, we found that testing this additives, that is to say both the lignin and polymer-based was more appropriate. Also because, as far as I remember, I hope that I remember properly, the use of the solution that you are mentioning is more suitable for when it comes to create a bound layer. I mean, when you're talking about wearing and when you are talking about the wearing course, if I'm not wrong. But actually, we did have a thorough conversation with those guys, definitely. And yeah, we found out that it was not suitable to use the Additive as well to make this research.
Okay, we have one more. I think we need to go quickly. Lignin lower the strength of clay might be in the consideration if there are clay in the subsoil.
Well, thank you again for this question as well. Well, as mentioned, I found a very wide literature when it comes to the lignin, and actually it was used in clay and filthy soils, and the results were pretty much awesome. I mean, it was possible to stabilize filthy and filthy soils with lignin. So I didn't find any kind of cons when it comes to the use of lignin in the clay and seals. And anyway, we didn't find any kind of cons or negative effects when it comes to the use of lignin in the crouch rocks as well.
Okay, thank you, Diego.
Thank you very much. And to the audience, thank you very much.
Yes, could I also just use this opportunity to remind everyone that on the 15th of March, we will have a presentation on early contractor involvement, which could be useful for a few of you, by Paulos Undimiu. So I would welcome you all back at that time. And then I say thank you for now, and I will stop the recording.
Thank you very much. Thank you very much. Goodbye.
Goodbye.